Hello, welcome to microprocessor architecture. Today it's time to talk actually about the microprocessor architecture in our course of principles of assembly languages or microprocessors or machine-oriented programming. Okay. So first let's review once again what are the important devices, the important components of a computer. And once in a while, I ask students this question, and I get all kinds of answers. So something that the box that the computer is enclosed in, the packaging is the most important. Some say the power supply is important because if you're not going to eat anything, then you're not going to be able to do anything. Some say motherboard and so on because everything is plugged into it. But really, if we look at these things, I'd like to say that memory is the most important because this is where the data is stored, including the data that we are using, including the data that that represents the actual program that's going to be executed. So that's what we need to to process. And then of course there's the processor, the CPU, I'm going to call it the central processor unit. That reads and writes from the data. Those are also this is also obviously, it's like the brains of the computer. But the thing is that without the data, without the instructions, the processor is pretty dumb. Let's be honest about it. Okay. So what processor does, it fetches the instructions, it interprets them, and then it executes them, and then it perhaps reads some data from the memory. Then it writes some data to the memory, and that's all it does. So for the processor, it's, every instruction is like a brand new day. It's like a duck, right? It doesn't remember much before. It doesn't know anything about the future, really. It just takes one instruction at a time and executes. All right, so the data, the memory is often called RAM, meaning the random access memory. Sometimes you also can see ROM or EEPROM for read-only memory, or electrically or erasable programming memory, or electrical erasable programming memory, even EEPROM, and so on. But the whole idea there is that this is like an array of bits and bytes that stores the information. There are other devices surrounding this ecosystem as well. Quite many of them are actually talking directly to the memory. Sometimes there's this thing called DMA, Direct Memory Access Controller, or just a memory controller, MC, that allows other devices to talk to the memory directly. For example, if you have a sound card in a computer, it may just take data from the memory and play it, as it goes on. And then when the buffer is empty for the sound card, then it may rise an interrupt to the processor and say, hey, well, I'm out of data. Could you give me some more? And then the processor prepares that next bunch of musical sound or whatever it is in the buffer for the sound card. And then the sound card can again happily read and play again. And the same for many, many devices that they talk to the processor actually through the memory. That's why the memory, I would say, is the most important device, because it's in the center. Now, in this course, we are going to learn about programming in assembly language, how to make the processor do the right things, and what the environment is on the processor for us programmers so that we can actually do the right things in the most efficient way. That's what we are learning in this course. So, random access memory. Why random? So random in this case means that we can actually pick any location that we want to go to and access that location. Okay, so this doesn't mean that, at random I'm imagining a number and that's where I'm going. No, I'm going to a targeted, very specific address that I choose to go to. All right? That's the benefit of random access memories. There are other kinds of memories. For example, there are sequential memories. There are memories that are like a long string of bytes that you can write on one end and read from the other end. So it's like a queue, right? Then there are cyclic memories, sometimes used as a video buffer that you can write at certain locations, but they are being read out sequentially as they are being painted on the screen. For example, the data is being painted on the screen. and other versions, there's associative memories and so on, right? But the basic one is the random access memory that pretty much every computer is using. The way we can look at it, we can look at it as a long string of bytes, and every byte has its address, right? So this is the memory. It starts, let's say, from the address. Now there's a big question, should I start from the bottom up or the top to the bottom, right? So I could say that at the bottom we have address. Actually, no, I'm going to start from the top down, because that's how usually we write in English and read as well. So let's say we start from the address 0 and then we go forward until there is address, I don't know, FFF something, right? So this is a very short address that I have used. That's only 4 hexadecimal digits, so that's 2 bytes. So, which means it's 16 bits. So, which in turn means that there are 2 to the power of 16 addressable units in this memory, bytes. And each byte is 8 bits, as we learned earlier, right? So this is not a very long memory. Some microcontrollers may have that, the smaller ones. So how much is it? So this is something like roughly 64K kilobytes is the size of it, right? Because it's 2 to the 6 times 2 to the 10, and this is 124, and this is 64, right? So that's how we arrive to 64 kilobytes. So nowadays, of course, we're talking about the computers that have gigabytes of RAM or even a terabyte. So we need way more bits for that, not just 16 bits. And that's why we're talking about 32-bit addressable, or maybe even 64, or towards 64-bit addressable memory spaces. But the point still remains the same. We can access a random location by its address, and at that location we expect to have a byte, 8 bits. Can we access less than a byte? Can we access like the 3rd bit of a byte? Not really. Typically we cannot. There are some microcontrollers though that allow you to access certain bits that are usually used to control some aspect of how those microcontrollers work. But quite often this is organized so that you can still address the whole byte. The byte has a bunch of bits, and then you can individually mask the bits that you're interested in. Right. So generally it's impossible to access less than a byte. However, there are some systems that are word addressable, meaning that for each word, rather than for each byte, there's a single address. And word could be 4 bytes, it could be even 8 bytes for 64-bit words. Right. But for those computers, while we are saving some space in the addressing field, we can use less bits to address larger memory. We are losing the ability to actually address smaller chunks of that word. So for example, what if we need to store only 1 byte? We're still gonna have to use the whole word, because that's what we can access, right? So that's how it is. And the lowest address, the address starts from 0. We're not going to negative addresses, right? The address is unsigned always, okay? And then in some systems you are not allowed to use the 0th address because it's used for specific purposes such as the interrupt vector table or whatnot. In some systems, the program actually starts from the address 0, right? When you reset the system, that's where it's looking for the first instruction. So this is very processor dependent, how it is and where does it start. All right. Are there any questions maybe? All right, if there are no questions, then let me reiterate the obvious that you all know, hopefully, that 1 kilobyte is 10 to 24 bytes. 1 megabyte is about 1,000 kilobytes. 1 gigabyte is about 1,000 megabytes. 1 terabyte is 1,000 gigabytes. And then we can talk about petabytes and so on, right? 1 petabyte is 124 terabytes and so on. Now, this is what we use to measure the amount of memory, the size of the memory, meaning the size of the buffers or the data or the available storage and so on, right? But we have to be kind of careful because these are not exactly correct names. Because if we're talking about grams, then 1 kilogram is 1,000 grams. It's not 1,024 grams, right? However, in bytes, we kind of call them kilobytes, although we are talking about, 1,024 bytes. So the reason for this is because it's nicely equal to 2 to the power of 10, right? And then then we can talk about that. Oh, if we're talking about a kilobyte, then we can address that using 10 bits. If we're talking about a megabyte, then we can address that using 2 to the 20 bits, which is more than a million actually, right? But technically it's not quite correct. So sometimes you may have heard about the term kibibytes instead of kilobytes. That's when you are trying to be more specific, whether you mean 1,000 or 1,024. So that would be more correct, but it's not so convenient. And in the world of programmers, in the commune of pure programmers, usually when we say kilo, we mean multiply by 10 to the by 1024. But that's how it is. What can you do? Let's talk a little bit about how do processor and memory talk to each other. What's their relationship, right? So the processor, CPU, and the memory are the two main components of a computer, I would say. Right? So for the processor, in order to access some data, it needs to send the address first to the memory to tell the memory, hey, I want data from that address. And then depending on whether it's gonna write or read, it's gonna either send the data, and then the data will be written to this address somewhere, right? So data, the address shows where to save it, and the data shows what to save it at that location, right? And if we want to read, then of course this data can also go the opposite direction, right? We can read from that, right? But I guess the important bit here is that we need to provide this address. From the CPU needs to do that. And we're going to see that when we talk about the assembly instructions for data storage and retrieval. Also, it's good to understand that, if the processor needs some data, it doesn't happen like this in one step. It's usually 2 steps. First, you provide the address, and then once the memory has the address, then it gives you the data. Okay. If you want to write something to the memory, then maybe you can provide both, and it happens at the same step. I mean, there's more to talk about, actually. We could talk about the memory architecture, where the fastest memory is a register, and then we have cache memories, and then we have RAM, and then we have some sort of storage, such as hard drives, solid state drives, for example, and then we may have CDs and DVDs, then we have tapes, and then we have paper, and then we have rock, and then we have what else you have, right? Rock tablets, for example. But usually, up to a point, this architecture means that the higher we go, the faster the memory works, speed. But also the more expensive the memory is, right? Now, the lower you go, the more size you have for the same cost, or on the same area, or in the same volume, so to say, right? So when we're talking about this interaction between the CPU and the memory, probably what the CPU is going to talk to is actually the cache memory. That's what's happening under the hood. And then the cache memory is going to talk to the RAM, and there might be several levels of cache memory and so on, right? So that's the reality of the things. But we're going to abstract away from that. We're going to assume that CPU talks directly to the memory, and we're not worried about what's going on in the memory. All we know is that when we provide the address and the data, that is going to be written in that location. Okay. Now, there could be more options. There could be other ways how to, access data. There is this associative memory, for example, but that's not the subject for this class. Okay, we're gonna keep it simple here. The addressable space. So in the picture before, we had the CPU that sends an address to the memory, RAM. And usually when it sends the address, we need to know how many bits are we going to send there. It could be a 16-bit address. So if it's a 16-bit address, then how much memory can we address? How much memory can we access? The answer is 2 to the power of 16th, right? You could imagine it's like a table, and it has indices, and all of those indices, those are the addresses. And which means that there are altogether 2 to the power of 16 rows in this table, and then each cell of the table actually holds 1 byte. That's our memory, more or less. All right. So what if we need more memory? Well, if we need more memory, then we need more bits for the address, right? And we can go up to, there are different examples of architectures here, right? So some 20 plus years ago, Intel 8080 was released, and we could address 64 kilobytes because we used the 2-byte registers at the time. And that's how much, you could fit in 2 bytes with 16 bits. But then there were some tricks. People would use 2 registers and interleave them like this and get to the 20-bit addresses, shift 1 register by 4 bits and add to the other register, the so-called segment register and the index registers, and get to a bigger memory, addressable and so on, right? And then people still understood that this is no go. We need wider registers. And then eventually people moved to 32-bit registers and then 64-bit registers. And this way we could access much more memory and do the things we wanted to do with all this memory that we finally have access to, right? But before that, during the earlier times, there had to be all kinds of tricks played with the memory. You would logically separate memory in certain sections. I don't want to call them pages because pages are usually used when we talk about virtual memory. That's a different story. I believe you have talked about it already in the systems programming class, right? Okay. And right. And nowadays, we're using easily 64-bit registers or even 128-bit registers in certain architectures. This allows us to access more memory. This also allows us to hold bigger numbers in the registers, because usually this addressable space, these bits go hand in hand with how big the registers are. We are going to use the 32-bit registers and 32-bit addressable space because we are talking about ARM processors in this course, right? So that's going to be our focus, but we could have different sizes and options as well. All right, so let's see what the processor's responsibilities are. So when a processor is about to do something to run our program, I said before, it doesn't know what the program is. All it can do is first it needs to read an instruction from the memory. So there's a memory and there's a program somewhere here. And there's this called instruction pointer, or sometimes it's called program counter, PC. Essentially, it's a register that points to the current instruction. It has the address to the current or the next instruction. We're going to talk about it a bit more shortly. But essentially, the first thing, if we want to do something, we need to read the recipe. We need to read what to do. So therefore, we call this a fetch. The processor fetches the instruction. Once the instruction is in the processor, if you will, and for the ARM, instructions are 32 bits, right, or 4 bytes long. So all of these bits encode something to do. Usually there's the instruction type. There could be a source register 1, there could be a source register 2, there could be a destination register, there could be something else, there could be a value in the medial value and whatnot. So this information needs to be extracted from this 32-bit word, if you will, right? That's what the processor does. It does instruct it. It decodes the instruction, right? It understands, if you will, tries to understand, tries to get out the meaning of it. And once it has figured that out, then it already knows that I need to take this register and that register. I need to add them up together. I need to write the result to that register. And that's what I'm going to do. So that's called the execute stage of the processor. So during that stage, many things can happen. So the data can be moved within the CPU from one register to the other register. Often when I'm thinking about the processor, let's see, this is the CPU, I'm thinking that somewhere in there, there's this so-called register file, where I have register 0, register 1, register 2, let's say register 15. If we had 15 registers, that's what I'm thinking. And that's like the local, really very fast memory of a processor. And it can move the data between these registers. It can move the data to the ALU, arithmetic logic unit, so-called, right? And ALU is a digital device that can add or subtract or do some ands or ors or nots or some other operations with this data, and then this data can be written back to the register file. So this is kind of one way how to look at what's going on within the processor, right? And then the actual instruction is being decoded in the instruction register, IR, and then there is this instruction pointer or program counter, instruction pointer, program counter, which is also a register somewhere there. And that one holds the address that's going to be executed, right? Instruction register holds the addresses in that local memory basically selects which registers are going to be read and written, and also what operations are we going to perform on the ALU. Okay. So you can actually draw a nice little diagram that represents the inner workings of a processor, and we do that in some other courses, and actually even build the processor using some development kits. But here in this course, we are just programming the processor at a very low level. So flow control is another thing that can happen. So what that means is that by default, the program counter is going to skip to the next instruction after this instruction has been executed and read the next one, right? But sometimes we want to do loops where we're going to jump back and iterate over some piece of code and then again and again, or call a subroutine, so jump to some other location. Let's say we have a function somewhere here. We want to call this function. We need to jump over there. So that's called the flow control, right? How the instructions flow, how the program flows, the execution of the program flows. It could be sequential, one by one, word by word, instruction by instruction, or it could loop, it could jump, it could call some other instructions. Okay. Working with memory is another thing that needs to be done. So in this case, we are our processor, it has the local memory, but it's not enough really. We may need way more data. We need some external data. We may need to talk to some other devices through the memory. So we do need to work with the memory. So that would involve loading and storing data to the memory, right? And then there are some so-called privileged operations. So there are some instructions that are not available for just anyone on that computer, right? So those are being also provided by the processor. Those could be related to how do you configure the virtual memory, how do you protect the memory, how do you make sure that if you have several programs running in that memory that they are not allowed, so that they could not write to the other program's memory, how do you configure that, and so on. Okay, so these are the basic things that the processor does. The registers. So as said earlier, it's like a local memory for the processor, really fast, but also expensive. So they are at the top, and they are expensive in terms of how much size do they take up on the chip, and also how much energy do they require if we want to deal with them, probably, right? But they are fast, so they need to be fast in order to be useful for the processor that is fast itself. So they are not related to the cache memory or other local memory. So the cache memory will be somewhere below in this pyramid of architecture of memory. The size of the registers depend really on the CPU. The early processors would have 2 bytes. And actually, some smaller microcontrollers still have 2-byte registers, which is sufficient for the particular tasks that they are performing. Some others may have 2, 4, or 8 bytes. This must be OR. You could have an architecture that has a bunch of registers that are actually different sizes, different purposes. ARM registers have 4 bytes usually, so that's 32 bits. That's what we're gonna use. And there could be more and more new architectures, and even not so new architectures, that are using wider registers. There's even this architecture that's called very large instruction word architecture, and you can have 128 or even larger registers there. And one way to deal with them is, well, it's not necessarily because we need such big numbers with so many bits, but you could actually do things in parallel. You could fit, I don't know, 4 numbers in one register, and then you could do in parallel some operations, this register with some other register that's just as large, right? So that's what you do with very large instruction word architectures. When you have a lot of data that needs to be processed in parallel, for example, such as the multimedia data. You know, a picture has a lot of pixels. For each pixel, you need to do the same thing, perhaps, right? So then these kind of architectures are useful. The register classes, meaning, are there different registers? Are they the same? Let's call them the general purpose registers, because in ARM, you have most of the registers are pretty much the same. You can pick and use any of those registers for any task, right? At your convenience. So let's say there are the low or so-called non-shadowed registers. So when I say shadowed means they have a possibility to have a duplicate. Meaning that you could have 2 instances of the same register. And sometimes it's convenient because when you call a subroutine, for example, that does the interrupt processing, you do not want to waste the time to save the old value of the register, then use that register in the subroutine function, and then to restore the value. So that saving and restoring takes time. So you could save that by having just a shadow register, and you use the shadow register instead of the original when you do this subroutine. Then you could have the high registers that are only shadowed in so-called fast interrupt mode. FIQ, that's what it stands for. Those are the R8 to R14. So I should say that we're going to talk about the registers that go from R0 till R15. That's all the registers we're going to use in this class. Plus the so-called CPSR. I'm going to talk about that in a moment. Then you have the 13th and 14th register shadowed in most modes. Whatever that means, it doesn't make much sense right now, I suppose, but that's okay. What should make sense and what we should try to understand, that there is the 13th and 14th registers that have special purpose. Technically, they are the same, but they are used for special purpose. For example, the R13th is usually used as a stack pointer. So stack is a data structure where we can, for example, hold the parameters that we want to pass when we call a subroutine, when we call a function. Then there is this link register. So that register is being used when we call a subroutine, when we call a function. We need to know how to go back, right? So if we have memory here, RAM, okay, and this is our program here, and we have gotten this far, and now we want to call this subroutine, this function, and now here there's this return at the subroutine. We really want to somehow be able to return to the next instruction from where we call that one. And from that guy, for that purpose, we are gonna use so-called link register. When we call the subroutine, the link register actually holds the address to the next instruction, so that the return statement actually could go to that address. That's the purpose of the link register. And then finally, the program counter is the one that counts, you know, the instructions that actually holds the address for the instruction that we need to execute. All right. Okay, so CPSR, Current Processor Status Register. So this is a register that actually has a bunch of useful bits that we are going to use. Those bits are like flags that are being set if something happens within a processor. For example, if you add two numbers and the result is too large to fit in the register, you're going to have the overflow flag set. If you subtract two numbers and the result is 0, you're going to have the 0 flag set, which is going to be useful when we're going to want to check whether two numbers are equal. One way to figure out whether two numbers are equal is to subtract them and then see whether the result is 0 or not, right? Okay, and so on, and a few other flags. There are going to be 4 good flags for us to use. Altogether, there is actually more than 37 registers, counting, various shadow registers. But in any mode, we have 16 registers accessible plus the CPSR register, right? And each register is 32 bits. That's 4 bytes. That is also good to remember. Are there any questions maybe at this point? Okay, I hear no questions. Well, then let's move on. So modes. The processor, it can have different modes. So what does it mean? If you're thinking about a car, for example, right? When you drive a car, the car also may have, there are cars that have, the commute mode where it's nicely ramps up the speed, it slows down nicely, it's nice and comfortable car. Or it could have a sporty mode where it's like has a very fast acceleration and it's handling the turns somewhat, differently perhaps, So the same machine can run in different modes. Similarly, the processor has different modes. And there are some of those listed. Right? So from the systems programming class, I hope that you remember that in the operating system took advantage that the hardware can be in the user mode and in the kernel mode. In the kernel mode, everything was allowed for the program, and the responsibility was very high, of course, for the program, because you cannot afford to mess up, because you have access to everything, right? Now, in the user mode, that's usually how the programs run, the simple tasks, that can only live in their own memory, if you will, that do not have access to other memories, or do not have access to the privileged operations. They just do their own thing, okay? And if it goes wrong, then and tries to do some of those, let's say, privileged operations, then there's going to be an interrupt, and we're going to be able to actually catch this problematic situation. Right? Okay. So, therefore, there's this user mode, as described. There's the system mode. That's usually used for the operating system tasks, and it has some more options, but it is using the registers that are accessible in the user mode. Right? And then there is the supervisor mode. Sometimes it's abbreviated as SVC. That's a sort of the privileged mode where you can actually execute system call. So system calls are functions usually that the operating system provides, right? And in order to implement those functions, it needs access to hardware, for example. You could have a system call that allows you to write data to a disk, right? And for that, you need access to the hardware, the disk hardware somehow, right? There needs to be a driver written as part of the operating system that will do that, right? There's this abort mode that will provide memory protection and virtual memory. There's undefined mode, but that's allowed to emulate some other things that are not built into the processor. For example, you can emulate a coprocessor that in software that is not really there in hardware. What is a coprocessor? So that's an additional piece of hardware that does some things really well and perhaps really fast. You could have a square root, for example, as part of a coprocessor. Or you could have a program that calculates the square root using Taylor series or whatever other method, right? So the program will be longer, but what if your hardware does not have this coprocessor? Then you're still going to need a program that emulates it. So that's where you can use this undefined mode. There's this interrupt mode, or sometimes called IRQ. That's the interrupt service. So whenever an external device needs some help or has some event that it needs to tell to the processor, then it sort of knocks at the processor like, hey, I have something to tell you. And then the processor, when it has time, goes to that interrupt service. So it puts the rest of the programs that it's running on hold and moves to the interrupt service mode. And that's when it really quickly, hopefully really fast, so that the other programs do not have to wait for too long, services this thing that happened. For example, when I push the key on the keyboard will create an interrupt. In the x86 processor world, it's going to be the interrupt number 9. And the processor is going to see, oh, this is the keyboard interrupt. That means I have to go to the keyboard hardware, fetch the code that for the key that was pressed, put it in the keyboard buffer, and maybe notify some things in the operating system that there's a new key available, right? And then it goes back to the programs that it executed before. So it needs to be fast. That's why it has the specific mode with its own R13 and R14 and the flag register, the status register. And then there is this even faster interrupt service that will also have R8 till R14 registers as shadowed, so that it doesn't have to save if it needs more registers than just one, let's say. Then we may use the fast interrupt service mode. So these are all kinds of modes that the processor can be. We're going to concern ourselves mostly with the user mode, right? Because we're going to do simple tasks in this course, and we're not going to go into the privileged world or advanced world. All right. Any questions, perhaps? Okay. If there are no questions, let's move on. So let me talk about the architectures a little bit that the processors are usually built based on. And the two classic ones are the CISC architecture, which means the complex instruction set, or RISC, which means the reduced instruction set. And the idea for the complex is, one of the main ideas is that we are going to have instructions that are very smart. They can do a lot of things in one instruction. For example, you can have an instruction that copies the entire string from one place to the other place. It's going to have to loop through all the bytes in the string. We're going to have to provide memory address for where the one string starts and where the target buffer is. But it can do it. Okay, so that was the philosophy at the earlier days of the computers. That's actually how the x86 architecture was created and still works, so to say. Now later on, they came out this crazy idea about, why don't we kind of simplify everything? Why don't we just dumb down everything? We're going to have very few instructions, very small ones, and all of them are going to be the same size. All of them are going to, hopefully take the same time to execute. And we're going to have better computers. And then from the first world of the CISC, people may say, yeah, well, the simple instructions, you're going to have a lot of simple instructions to do the thing that we are doing just in one instruction. How can you be better than us, right? But then the RISC people say, well, this is the risk you have to take. Because when we have smaller instructions and regular in size, all instructions are regular in size, all of a sudden what we can do when this is time for one instruction, we can cut this instruction in several stages. Instruction fetch, instruction decode, execute, write back, and perhaps memory phase, right? And the thing is, we can actually start overlapping instructions. In the CISC world, we would probably have to wait for while the first instruction completes until we can do the second instruction, before we can do the second instruction. In the RISC world, we can overlap. We can start the next instruction before the previous has finished. So the previous is done with the instruction fetch. Now this can do instruction fetch, and so on. And then another one, and another one, and another one. And all of a sudden you can see that you have 5 instructions in parallel, executing in parallel. So they say, yes, we're gonna need more instructions to do the same thing, but we can do them sort of in parallel, and that way we can save time. And we can do it only because we have fixed length instructions, so that means we can always predict where is the next instruction. We do not need to complete the instruction to see whether the next one is going to be short or long, and so on. We can, plan better because we know how long everything is going to take, and so on. So that's the main advantage, I would say, for the RISC architectures. That also gives us better performance. It also makes chips smaller and cheaper. And sometimes when the chip is smaller, you can actually run them faster, right? Because for the CISC architectures, sometimes you have to take the worst case scenario to figure out how fast can you really run it. And turns out you cannot run it that fast for all the instructions. You're going to have to slow it down so that the complex instructions can finish in time. For the RISC, all the instructions are small. They all complete very fast. And there's this advantage. All right. So there in this slide, you can see that the key points on the difference, the CISC is emphasis on hardware. Let's do everything on hardware. In RISC, it says, okay, we can do everything in software if the hardware has simple instructions, but are very efficient. But is very efficient. Right? Here you have the single cycle instructions, meaning that every instruction sort of completes in and maybe you have a cycle per step, right? While in CISC architecture, you may need multiple cycles for some instructions to finish. For example, if you are copying a string and the string has 100 bytes, then you're going to need at least 100 cycles for it to finish. Complex instructions for CISC architecture versus simple instructions. We did talk about that. In CISC architecture, you may have the arguments for the instruction that point to the memory. You may have, like when you copy 2 strings, you need at least 2 pointers to the memory for the source and for the target string. The RISC architecture is register to register or R to R in architecture, which means that there are only 2 instructions that deal with memory. One is to load from memory to a register, and the other is to store from the register to the memory. And that's it. That's the only thing how you can talk to the memory. Seems very restrictive, but it really simplifies, the things that you can, the whole world and architecture, which means that you can actually predict its performance better and you can optimize it better. CISC architecture may have smaller code size because the instructions are kind of, smarter, if you will. We're going to need more instructions for the RISC architecture. But the advantage, I guess, for the RISC architecture is that because we have smaller instructions, we're going to use more transistors for the memory, and we can have more memory on board, more cache memory, more fast memory, which again makes that processor faster. While the CISC architecture just focuses on implementing these complex instructions, and there's not that much space left. Okay, so here's the example. We can have a multiply instruction for multiplying 2 arguments from the memory, and that's just one instruction. We may need 4 instructions for that from the RISC architecture: load, multiply, and store. Right? But the time to execute that is going to be following the following formula down below. Well, it's how many seconds it takes to run the program, or how much time it takes to program, which really boils down to how many instructions do we have in the program times how many cycles per instruction do we have times how many seconds do we have for the cycle, right? So even though at the first sight it means it looks like, oh, one instruction, this is going to be much faster, right? Not necessarily. So this instruction is going to take longer time. It's going to take multiple cycles to perform. While here we're going to have 4 instructions. Each of them is going to take just 1 cycle. And since the instructions are smaller, each instruction is going to take much faster. Each cycle is going to be much smaller than the cycles here, perhaps. Right? So there is a real benefit for RISC architectures nowadays. One might say, well, how come we don't have all the computers as RISC computers? How come there's still x86 around? And one big thing is this legacy, if you will. There's a lot of software written for x86, and a lot more is being written with every day. And people are just not ready to throw away that software. And as long as there are companies that provide support and hardware, people are just going to buy those computers, even though they might not be the most, efficient way. On the other hand, there are RISC architecture, RISC processors. For example, Apple somewhat recently switched to ARM processors for their laptops, and ARMs are RISC architectures. And to be fair, I also should say that the modern x86 architecture processors, they are using the microprograms and pipelining and all kinds of technologies inside to implement this old legacy instruction set. So they may, under the hood, also run kind of like optimized architecture. And that's how they are capable of keeping up with the rest of the market. All right. Maybe there's a question or comment. Well, let me move on then. All right. So let's look at the processor tasks once again. Okay. How do we fetch the next executable instruction from the memory? So remember, there's CPU, there's the memory. The CPU is using the program counter PC register, and as we learned, actually this is register 15 for the ARM architecture, and that's going to store the address for the next instruction. It's a bit more complicated than that, but let's just assume that's the next instruction or something like that, right? We're gonna talk about it shortly. So once we have fetched that instruction, then the PC is gonna execute that instruction, and then it's gonna advance the processor is going to execute that instruction, and it's gonna advance the program counter to the next instruction. Right, as discussed a little while ago. So, ARM processors do not change the data in memory directly. So that's about the RISC architecture having only loads and store instructions. Right? And ARM does not do double referencing, if you will. Does not use memory to access another location in memory. If you want to use this kind of thing, then you're going to have to load the first memory location to a register, And then you can use this register to point to a different location in memory and access data from that memory. So you could do it that, but you cannot do it in one step, right? You would need to have a little program for that. Okay. And that's how it is for all RISC architectures, right? So the point was to allow for simpler and faster instruction sets. Now let's look at the CPSR a little bit. Okay. So once the instruction is being executed, so let's say we need to add two numbers, the flags are going to be set. If there's an overflow, there's going to be an overflow flag set. If there is a 0 as the result, there's going to be 0 flag. If the result is negative, there's going to be the negative flag set, and so on. All right. And those flags can be used by other instructions that are coming later. That's one way how to implement the if statements in higher level languages, for example, checking those flags. And then the PC, the program counter, is being incremented. And as I promised, it's a little bit strange for ARM architectures because it always points 8 bytes ahead. Okay. There are some technical reasons for that, but that's how it is for ARM architecture. However, if you look at the debugger may actually show you as if the PC points to the next instruction. So this is a little bit misleading, but it's useful from practical purposes, right? But if you are reading the PC directly and using its value in its calculations, you have to know about that it's 8 bytes ahead. It's not just the next instruction. Fun fact like that. Okay, so the processor does not execute the program, of course. It does not know about the program, it just knows about the instruction that it executed. There are some tricks, though. The processors may do branch predictions, for example, or some other tricks to optimize the performance, trying to guess what's going to come next ahead based on the previous history. But we're going to talk about it when we talk about the optimizations of the code, right? So here's an example of the assembly code. So there are 5 instructions. Okay, so these are instructions. And these are, guess what? These are also the instructions. Except they are encoded. They are compiled. This is a 32-bit instruction word that represents this instruction to the right. So what we're going to do in this course is we are going to write assembly programs like this on the right side, and they are going to be compiled to the machine code like this one on the left side. So this doesn't mean that you have to be fluent in all these digits and numbers and so on. But so this whole is a listing, by the way. And you can get this printed out from the compiler, if you will, if you want to. But sometimes it is useful to see what kind of code was compiled from your instruction. What you really may find useful is the address. So this is the address at which the instruction is in memory, right? And sometimes your code may use that address to actually, I don't know, access some data or maybe jump to a certain location, and so on. So that's the anatomy of a listing. Now for the instructions, usually there is this name of the instruction, such as move. And then you have the parameters here. And different kinds of instructions have different parameters. Here move means that you're going to move from the register 3, you're going to move its value to a register 0. So it's actually going to be copying the value. And here add means that you're going to add R2 plus R3, and it's going to go to the R3. Load register, LDR, so that means we are loading the register from the memory location, And the memory location could be provided using the SP, the stack pointer register, that +4. So you can sometimes do some arithmetic for the addresses, which is convenient if you want to access the array elements, or that you want to access parameters, for example, in the stack that are being passed to our subroutine, as it looks like in this example. All right. So at this point, we do not need to understand what exactly is going on in this program, but just to give you the feel of what is an assembly program and how does it relate to the actual machine code, instruction words, and the addresses. All right. Questions? Maybe? Okay. So in conclusion, each ARM instruction is 32 bits long. Let's remember that. This is just as long as the register is for the ARM architecture, so that's also convenient. Instructions are executed in the order they are in memory, so this is a sequential execution. Every time the PC, the program counter, is being, incremented to the next instruction, to the address of the next instruction. And exceptions are, of course, when we have the control flow instructions, meaning that if we want to jump to a different address, if we want to call a subroutine, if we have a branch on the condition, if the result was 0, then we branch to a different location in memory. Okay. Now the functionality of the program depends on the order of instructions, right? So the order you write them, that's how it's going to be executed. In some higher level languages, it's not always the same, and even if it looks like it, the compiler may actually optimize the code by rearranging these commands, as long as it does the same thing. Now in assembly, these instructions are going to be executed as we provide them. And if you send the processor for the next instruction to the data region, for example, if we somehow get the wrong value in the program counter, then we may have an explosion, Well, not necessarily that the chip is going to explode and burn and things like that, but you don't know what instructions. Usually in the data area, you have the data. You do not have programs. Maybe you store the variable data, you stored 7 in a variable, value 7, right? Now all of a sudden, if the PC is going to point to that variable and the CPU is going to think, oh, there's instruction, let me load it in. It's going to load that instruction. What's the code? It's 7. So let me try to decode it. And it could be that it's going to be an illegal instruction. Then you're going to have an exception. So that's a good thing. It could be that it's a privileged instruction. You're also going to have an exception. At least your program is not going to move forward. Or it could just randomly happen to be a valid instruction that's going to all of a sudden mess up something else in your code. It's going to jump to a random location. It's going to mess up the data, or I don't even know what's going to happen. So beware, right? Stay in the program memory, which is called the text segment. And there's also data segment. Stay away from the data segment when you're dealing with the program counter. Okay. Better yet, let the compiler to figure out what the addresses should be and what the value for the program counter should be. All right. Now, let's look at the x86 architecture a little bit. So x86 is different from the ARM in one way, such that it has a very specific registers. They're not all equal. They can even be in different sizes. So for example, if I have the so-called AAX, extended AX register, then we can divide it in, the lower half is actually AX, which is also divided in A high and A low. So you have 4 registers pointing to the same location more or less, right? And the reason for that is the historic, because we started out with 2 bytes, and then we moved to 4 bytes, but we still had to be able to run the programs that use the old programs that use the old registers, and then we moved to even more bytes, and we need to use the big registers, but we also need to use the small registers for the older programs and so on, right? So that's one difference. The other difference is that the registers are very specialized. For example, AX is the accumulator. So that's usually where the result of an operation is stored. When doing arithmetics, for example, right? You can store it in other registers as well, but this is more of a convention. Now, BX is usually used as a base register. So for example, if we need to access some data from one address that we're going to consider a base, then B is going to hold the address of that, likely. CX is often used as a counter register, and there are certain instructions that assume that by default, and there's no way to change it. DX is often as a data register, and each of those have those, EAX or high and low versions of the registers. The next 3 are the segment registers, which historically were used to access memory that's farther away. Remember I was talking about the registers that were sort of shifted by 4 bits in the beginning, so those are the ones. But later they were repurposed to hold some service information, such as the protection bits and access information. So those are called the segment registers. Very special. Sometimes, now I'm thinking, can you even write to them? In some modes that could be restricted, right? The stack pointer, well, we have stack pointer in the ARM, but here the stack pointer really is only used for the stack, for referencing the data in the stack data structure, right? And instruction pointer is the same as program counter that we're calling in ARM. It's just a language issue. But again, it's a separate instruction, and I don't even think that you can directly read or write to it with some other instructions. I might be wrong, right? So it's a very, very, different system. It's not regular at all. And the instructions may be of different lengths. You can have very short instructions and very long instructions as well. And I'm not talking about the execution time, which is also an issue, but I'm talking about the size in the memory, how many bytes it takes. If they are in different sizes, it's very hard to implement this pipelining principle that I was talking about, to be able to actually execute them in parallel, potentially. Right? So that's the world of x86. But we're going to stay with ARM, and all registers are pretty much equal all over the place. 13, 14, 15 are a bit special, remember? So this was the program counter, this was the link register, and this was the stack pointer. But you can interchange the names in the code. You can use either one, right? CPSR is sort of a special register that's on the side because it has a bunch of bits that we're going to see in a little bit. R2 sometimes is used as a frame pointer. It's like a register with an address for the reference of the frame in the memory. Could be memory buffer or could be the variables, to simplify debugging, for example. But again, this is not something that's built in the hardware. This is more of a convention, right? The hardware is still regular and the same. But in general, if you're using registers starting 12 and above, be careful. Those are not meant by convention for simple calculations, such as, add 2 registers and see what happens, right? Because they may hold meaningful information, such as the stack or the link register. So in assembly, we can use special names for these guys. FP for the frame pointer. These three I wrote up above already, so that the programs are easier to read. Now, guess what? There are more registers that we're not going to talk much about in this course, and we're not going to use. So there are floating point registers, for example, right? So what's a floating point? If we want to write 1.234 times 2 to the power of 122, so that's a really large number that I could not fit in 32 bits. But using this floating point notation, I am able to, right? And that's why the architectures, the processors, there are some that have floating point, there are some that do not have. Makes them faster, makes them smaller, but they're not as efficient perhaps when you need to do some math, some, I don't know, simulations, for example. That comes in handy. There's a coprocessor perhaps. Remember I was talking about a piece of hardware that can do square root really fast. Maybe sinus, cosinus, trigonometry functions, maybe something else. Matrix multiplication maybe. So those could have their own registers that are somewhat special, right? They could be even different size. For example, if we are talking about matrix multiplications, how are we going to store the whole matrix in the register, or right? And the registers outside CPU kernel, so sort of the CPU kernel is like where all the action happens, but there can be some registers on the side as well. But those registers, they're like those unlisted. Remember there was this undefined mode where you could use some specific functions. For example, when you have a CPU, you have all the registers in there. But now I'm telling you that you could kind of have some registers that are sitting in the RAM. Okay. And when the instructions, the special instructions, access those, they're pretty much writing and reading from the memory. And then the memory, it could also be not the real memory, but it could be mapped to something else. That is actually some device. And it could be registers within that device. So the idea here is that in the program, we can easily write and read to the memory from the instruction point of view, right? And then the hardware can translate those to the actual registers in some other devices outside the CPU. And these registers are gonna define how that device behaves, you know. It could be just a register that holds bits that say whether the LEDs are on or not, on or off, you know, for some, I don't know, visualization. All of those new computers, they have LEDs jumping around within the boxes to make it pretty, right? Or it could be some bits that control how the sound card works, or how the video controller works, or something else. All right. And finally, about the CPSR, what are the bits? The size is still 32 bits. The bits that we're gonna care about are these 4. And the rest of them we're not gonna worry too much about. And the 4 bits are the negative. It tells that the last operation had a negative number as a result. The 0 bit, again, if we subtract 2 numbers that are of the equal value, that's gonna be set. The carry bit, well, what if we add 2 guys and, you know, the most significant bits are 1 and 1, then you're definitely gonna have a carry bit to report. And overflow when the result did not fit. So that's the information that we can get. So this being said, to recap, the major components of a computer are what? They are the memory and the processor, right? The processor has its own local memory in there that's called registers. That's a very fast memory, but very limited in size, right? There are 2 different major architectures, such as the CISC architecture and the RISC architecture. The RISC is kind of smaller, faster, but will ask for more instructions to write something. The CISC has complex, smart instructions, but it's going to be kind of big and bulky, perhaps, in terms of the processor. And as a result, the focus there is on hardware, implementing functions in hardware. For the RISC, the focus is on making everything in software using very small, very fast instructions, and devoting the rest of the space on the chip for the memory, and therefore having more fast memory and better performance. Okay. And for the ARM architecture, all the registers are equal, pretty much. We can add any two registers, subtract, do things like that. And there were those few registers that have special purpose, namely the program counter that always shows to where the next instruction is going to be. But keep in mind, it's actually not the next instruction. It's like the current instruction plus 8 for the ARM architecture, while the debugger may show the same thing. It's the link register that's going to hold the address from which we call the subroutine, so that we can return to that subroutine, to the next instruction after the calling one. And the stack pointer, so that we can pass the stack, we can pass the parameters to this calling to the functions. Right? Pass the arguments, I guess, the values. And then there's this frame pointer that's good for the debugger, but that we are probably not going to pay too much attention here. Now, the moral is, stay below register 12 and you should be safe with your calculations. This being said, my story is over today, and I hope this was useful. I'll see you next time.